in this video, we're going to discuss the von Mises yield criteria, which is used also for ductile materials. The von Mises yield criteria is also referred to as the maximum distortional energy criterion. Um, so what? So the von Mises yield criteria is based off of a concept called distortional energy. So I'm going to introduce what that concept is, and then we're going to show how you can use that to predict failure within a component. So in the case of if you have a stress element, which would be defined as being a cube of equal sides, and we apply 3 uniform stresses to it. So if we say that we are only applying uniform normal stresses. So we're going to say our 3 principal stresses, sigma P1, sigma P2, and sigma P3 are all equal. All right. So this would be a case of triaxial uniform stress. Okay. So if so the cube basically will remain a cube. Nothing will happen to it because all the stresses are normal. Okay. What happens though is if we change the magnitudes of any of the principal stresses, so if we change the magnitude of sigma P1, sigma P2, and sigma P3, the element is going to distort itself, so it's no longer going to be cubic. Okay, so basically, if this condition is true, our cube becomes a distorted element. Okay, which might be some type of rectangular prism. Okay, so for that. So what we can state here is that any state of stress we can define. So if we have an initial state of stress on a stress element, we can consider it to be the superposition or the sum of the hydrostatic stress state and the distorted stress state. So what we're going to define is we're going to define our hydrostatic stress, which we can refer to as our average normal stress, as being the sum of our 3 stresses along the x, y, and z axis divided by 3, which should be equal to the same as the addition of the 3 principal stresses divided by 3. So if we go to the next page here, right, we can take our given state of stress, right, and we can split it into the addition of our hydrostatic stress, which is just our average stress we defined on the last page, and then the distortional stress, right, which is just equal, so it's just equal to our original stress straight, with along the diagonals we have to subtract out our minus average stress, right? So in certain cases, if you already have your stress element has been already transformed to along the principal orientation, it only has normal stresses, right? So the hydrostatic stress would just be equal to the average stress matrix along all the normal directions, and then the distortional energy stress matrix just has the minus the average stress from each of the principal stresses. All right, so from these definitions, we can define the total distortional energy due to the applied normal stresses. So if we look at so we can define the distortional energy as being equal to this quantity here. You might wonder, how did we get energy from the state of stress? What we can do is, if we go back and look at a stress strain diagram. Alright, so on our y-axis we have stress, and on the x-axis we have strain, and we have our given curve here. Alright, so if we look at just the elastic region, alright, before we have any yielding, alright, and we look at the area under the curve, alright, we can approximate this area under the curve as being a triangle. Alright, so we can say the area under this curve is equal to 1/2 the base times the height. So we can say it's equal to 1/2 stress times strain. Okay, so we can plug in, we can use Hooke's law, and we can say that for an elastic material, the stress is proportional to the elastic modulus times the strain, and we can say that the strain would be equal to the stress divided by the elastic modulus. If we plug that into this equation, we end up getting that the area under the curve is going to be equal to 1/2 times the stress squared over this elastic modulus. Okay, so in this, so the last thing is that if you think about what are the units of this of the area under the curve, the units for stress are newtons per meter squared, and the area for strain is units for strain is meters per meter. So if you multiply those out, newtons per meter is the same thing as joules, which is an energy term, and then the denominator is meters cubed. So it's the joules per volume. So you can think of it as a specific energy. And so this area under the curve here, we'll call this is our distortional energy. So we can say UD. All right? So that was for a uniaxial case, but it can be extended out to a case of triaxial stress, which is how we can get this this term here. Okay, so if we take our distortional energy term here and we substitute in some of our some of these values for our principal stress, what we end up getting is a new equation for our distortional energy here, which is just a function of the Young's modulus, the Poisson's ratio, and our three principal stresses, sigma P1, sigma P2, and sigma P3. So in the case of a tensile test, we can say that we can set that at failure, our principal stress is going to be equal to the yield strength of the material along the tensile force direction. But then there's no other forces being applied to the system, so we can set sigma P2 and sigma P3 equal to 0. Alright, so if we do that, we can plug in all of our values for our distortional energy. Alright, and we can say that the distortional energy would be equal to 1 plus the Poisson's ratio divided by 6 times Young's modulus, and we would get sigma yield minus 0 squared plus 0 minus 0 squared plus sigma 0 minus sigma yield squared. Alright, so if we evaluate all that out, what we end up getting is we get 1 plus the Poisson's ratio over 3 times the Young's modulus, all times the yield strength squared. Okay, so so what we're going to do now is we can go to the next page, all right, and we're going to have the same relationship defined here for the distortional energy as a function of the yield strength of the material. All right, so this is the same equation we have here. All right, so now what we're going to do is we're going to plug in and we're going to solve for the yield strength in terms of the distortional energy and the Poisson's, the Young's modulus and the Poisson's ratio. So if we do that, all right, all we're going to do now is we're going to plug in our equation for distortional energy. So if we plug in our equation from distortional energy from the last page into our equation here, what we'll end up get is we'll get the yield strength is going to be equal to this following equation here. All right. So what we can do is we can define the right-hand side of this equation. We'll call this our sigma von Mises, right? And we'll say that yielding will occur on any ductile material when the von Mises stress is greater than S yield. All right. So if you're trying to use it for design, you can say that for a given material and for a desired factor of safety, the maximum von Mises stress has to be less than or equal to this value in order for failure will not occur as long as this inequality is true. Right? So, so in short, we can use this distortional energy theory and a simple uniaxial stress case in order to relate the yield strength to the von Mises stress, which we can then use to predict failure within an engineering component for any state of stress, regardless of how complex the loading situation is.